Alright, so now that we are done talking about all of our functional groups, we can now start putting all of these functional groups into bigger molecules. So the first bigger molecule we're going to be looking at are our carbohydrates in Chapter 16. So we have a few goals for Chapter 16. We're going to be looking at the boiling point of these compounds, being able to recognize and classify our mono, di, and polysaccharides, classifying our monosaccharides as aldoses or ketoses, and as trioses, tetra, penta, and hexoses. We're going to look at D and L sugars. We're going to mean what it means by anomers and describe how they're formed. We're going to look at mutorotation and physical and chemical properties of these monosaccharides. We're going to be looking at monosaccharides and that are needed to form sucrose, lactose, and maltose, and compare the contrast, the structures, and uses of starch, glycogen, and cellulose. So first things first, carbohydrates are also known as sugars. So just to get our point across, it's a little song. I'll listen to a little bit.
Oh, honey, honey, you are my candy girl, and you got me wanting you. Honey, oh, sugar, sugar.
Alright, that's enough. So, like I said, just to get the point across, carbohydrates are also known as sugars. So carbohydrates we're starting off with because it is an extremely abundant biomolecule. More than 50% of the carbon in organic compounds is found in carbohydrates. So we'll see that it's all of the cellulose, all of our sugars, it's found in a lot of molecules. So not only is it in the cellulose, but plants use photosynthesis to store energy in glucose, which is a simple sugar. So our photosynthesis gives us our carbon dioxide plus water plus energy, that's our sunlight, gives the plant some glucose and oxygen. So it's kind of cool that our byproduct of carbon dioxide is needed for plants, but then they produce oxygen as a byproduct themselves, and we need the oxygen. So we have that's why we need so many plants and trees. It's because we kind of have a symbiotic relationship here. They need CO2, and we need the O2 that they produce. So we'll be looking at this reaction a little bit more, but let's first start talking about our carbohydrates. So carbohydrates are sugar, but they're also naturally occurring polyhydroxy aldehydes and ketones. Remember, this hydroxy just means a alcohol group off of the main chain. So many alcohol groups with an aldehyde or ketone at the end of it, or at the end of the chain. So our simplest carbohydrates are our monosaccharides, also known as our simple sugars. And then the simplest carbohydrate containing 3 to 7 carbon atoms, so they're not very big. We're going to say that an aldehyde is going to be known as an aldose, and a ketone then is going to be known as a ketose. So you think of glucose, that's the sugar end of it, so the ose, aldehyde with the ald, and ketone with the ket. So aldehyde and aldose and ketose. So if we look at just our simple monosaccharide down here, we see that we've got some carbon chain that has an aldehyde at the end of the chain. That's what makes it the aldose. And here I've got some long carbon chain and a ketone at the end. Notice I still have alcohols at either end here and an alcohol at this end here. So these aldehydes are grouped into 3 classes. A monosaccharide, which we just looked at. These are the simple sugars, and they serve as the building block of our larger molecules. But they're kind of the ones we're most familiar with as well. So the example is glucose, such as the sugar found in our blood. So we're going to be looking at a little bit about diabetes this semester, just because it's very relevant to biochemistry. It's got a lot of chemistry involved in it, and it's kind of an epidemic in our country right now. So either type 1 or type 2, you're supposed to test your blood sugar. Well, what is the blood sugar? It's glucose that you're testing. So we'll see actually how these machines are testing the glucose here in a little bit. So our next classification is an oligosaccharide, which contains 2 to 10 monosaccharides. So you think of those monosaccharides, so you have 2 to 10 of them, and you've got an oligosaccharide. And we're going to say each building block is also called a residue. So when you hear a sugar residue or a monosaccharide residue, it's just each monosaccharide in the chain. And so another one we're familiar with is sucrose. So sucrose is an oligosaccharide. So our last one is a polysaccharide, which contains 10 or more of these residues. So 10 or more monosaccharides. And these are our complex carbohydrates. So these are a lot of ones that you see in fruits and breads and such. Alright, so we're going to take a look at each of these groups and categories in turn. So let's first start off with our monosaccharides. So these monosaccharides are polyhydroxide ketones or aldehydes with 3 or more carbons. So if we look at glucose, glucose has 1, 2, 3, 4, 5, 6 carbons. Notice that at the end of glucose, there's an aldehyde molecule. So glucose, it is an aldohexose. So notice I have hex, meaning 6. You see ose, meaning it's a sugar. Also notice that each of these last 5 carbons all have a hydroxide at the end. So we're going to see that these hydroxides, the position of them does make a difference. So this one being on the left and these ones being on the right do make a difference. So we're going to talk about all of those, changing all of those here shortly. So another one is our ribose. So you think of ribose nucleic acid RNA. So here's ribose. It's also a compound in ATP in our coenzymes. Ribose is 1, 2, 3, 4, 5 carbons with an aldehyde at the end, which makes it then an aldopentose. Another example then is 1, 2, 3, 4, 5, 6. So fructose is a 6 carbon chain with a ketone here at the end. So that ketone makes it a ketohexose. So 6 carbons and a ketone. So this is our corn syrup and fruit. Once again, this carbonyl group could be on either end. That does not make a difference, but it does make a difference where these alcohol groups are. So we'll be able to draw different, essentially isomers of these molecules. Now we kind of talked about the naming as we were going through our examples, but let's formally name these molecules. So the carbohydrate nomenclature is unique to our sugar chemistry, and we do not use name monosaccharides using our IUPAC rules. So they're going to be a little bit different. But monosaccharides just are going to end in ose, and they can be identified as either aldoses or ketoses, and then we're going to name the number of the chain. So is it tri, tetra, penta, etc. So it's an aldotriose or a ketotriose or so on. So we aren't going to name a particular molecule. We're just going to name, does it have an aldehyde or a ketone? How many carbons are in it? That's it. All right. So just to give you a chart with all of these, the 3 is still tri, tetra is 4, so we're kind of going back to our last semester naming. So tri, tetra, penta, or just pent, hex, hept, oct, non. Technically it would be dec too, but you don't really see dec because they just don't get that big. And then aldehyde is an aldo, ketone is a keto. So if there are 3 carbons with an aldehyde, it's just an aldotriose. 5 carbons with an aldehyde, it's an aldopentose. 7 carbons with a ketone, ketoheptose. So we're not necessarily naming a particular molecule, we are just kind of classifying it as how many carbons and what kind of functional groups are on that molecule. Alright, so if we were asked to name these 2 sugars, I see I have an aldehyde at this end, and it's 1, 2, 3, 4, 5 carbons in the chain, so it becomes an aldopentose. This one I've got 1, 2, 3, 4 carbons in the chain with a ketone, so a ketotetrose. All right, so let's give a few for you to try. So go ahead and indicate which each of the following is an aldose or a ketose, and then describe how many carbons there are. All right, so the first one, I've got a ketone and 4 carbons, so ketotetrose. Second one, I've got 1, 2, 3, 4, 5 carbons and an aldehyde, so aldopentose. I have a ketone with 1, 2, 3, 4, 5, 6 carbons, so ketohexose. Aldehyde with 1, 2, 3 carbons, so aldotriose. 1, 2, 3, 4, 5, 6 carbons with a ketone, so ketohexose. And 1, 2, 3, 4, 5 carbons with an aldehyde at the end, so aldopentose. Now technically that last line was only asking for whether it was a ketose or an aldose, but we named the number of carbons just for practice. Let's do both here as well. So this is just a different way of writing them, so instead of writing them top to bottom, we're just writing them left to right. These are actually make it a little bit easier to see. So go ahead and try these 3. All right, so this first one, I've got 1, 2, 3, 4, 5 carbons and an aldehyde at the end. So it makes it an aldopentose. I've got an aldehyde at this end and 1, 2, 3, 4 carbons. So an aldotetrose. And a ketone with 1, 2, 3 carbons, so ketotriose. All right, so let's start talking about moving those hydroxides around. So if we take our carbohydrate molecules that we were just looking at, and then we take the mirror image of it, we are going to call each one either a D or an L monosaccharide. Now, these isomers are different in spatial arrangement and are stereoisomers. Our stereochemistry is the study of spatial arrangement of our atoms, and we've already looked at it because we've actually already looked at stereoisomers a little bit. But let's talk more about them with our D and L glyceraldehydes. And these are non-superimposable mirror image molecules. So they are stereoisomers, and the type of stereoisomer they are, we are going to call enantiomers. Enantiomers are basically just the mirror image of that molecule. So let me give you an example. So the easiest way to think about a mirror image is if you take your hand, and then you take your right hand, you put it out in front of you, you take your left hand, you put it out in front of you. They are mirror images of each other. However, if you try to superimpose or you try to put one hand on top of the other, you can never make them look exactly the same. Your thumbs are on opposite sides. There is no way for your right hand to look exactly like your left hand. There is no way for somebody to be able to transplant a right hand onto a left hand and make it work. They are non-superimposable. They are two completely different hands. We could say the same thing with our enantiomers. So if I take the mirror image of it, I cannot superimpose them on each other. I cannot twist or turn these molecules to make them look exactly alike. I have to break bonds and then reform the molecule to get an exact mirror or an exact duplicate. Same thing with our hands. We'd have to break the bond of our thumb, stick it onto the other side of our hand to be able to make it an exact duplicate. So that is what an enantiomer is. It's a mirror image that you cannot make an exact duplicate of. So if we were to actually look at our carbohydrates now, the quote-unquote thumb of the carbohydrates is these alcohol groups in the middle of the chain. I would have to break off this alcohol and put it on the other side. There is no way for us to twist this molecule. So we're going to call these middle carbons chiral. Chiral means that they have carbon atoms carrying 4 different groups. So if I look at this carbon here, I've got a hydrogen, I've got an alcohol, I've got a carbon with an alcohol, and I've got a carbon with a carbonyl. So I've got 4 different groups hanging off this central carbon. Whenever that happens, it creates you can create an enantiomer if you take the mirror image. So the glyceraldehyde, the D version is going to be called right-handed. That is because the last alcohol in the middle of the chain is on the right. When I say it's L, it's going to be left-handed, or the last alcohol in the middle of the chain is on the left. Notice I say in the middle of the chain. I'm not looking at the alcohol at the end. This is because this one has 2 hydrogens on it. So it's not chiral. So it does not make a difference. This one we can twist. So we're not looking at the last alcohol. We're always looking at the second to last alcohol. So in this case, if it's on the right, it's D. If it's on the left, it's L. Now, it just so happened that Fischer, who is the guy that created these projections, these are actually called Fischer projections when we draw our molecules this way. Fischer projected that there were 2 different mirror image molecules. This was back in like the late 1800s. So he figured this out, and he happened to call them D and L enantiomers. It just so happened to work out that the L enantiomer always happens to be on the left, and then the D one happens to be on the right. So there was no real designation D or L. There's no a lot of meaning behind it. So he just called it, maybe Fischer had a meaning, but it's kind of been lost. So this is kind of just a traditional way of naming these, is D and L. Now there is another way to name these with R and S, and that has to do with kind of the spin or the groups on the molecule, but we won't need to worry about that yet. So talking about the physical properties of these 2 stereoisomers, they actually are very, very similar. They have the same physical properties, so they have the same melting and boiling points, except they behave differently in the way they rotate polarized light and the way they are affected by a catalyst. Catalysts normally work by where everything is connected. So if something's connected in a different position, the catalyst is going to not work as well. So that's why only one of these is biologically active. So I'll leave you hanging about which one, but only one of them will actually show up in our body. The other one does nothing because it does not, or it's not affected by those catalysts. What do I mean by optically active? What do I mean by it's twisting and turning or moving light around? Well, we're going to call all enantiomers optically active or optical isomers. So this is really one of the only ways we can determine which enantiomer we have, because their physical properties are the same. So what we're going to do is we're going to shine polarized light through the solution. So if we take a beaker of our solution and we shine some light through it, some plain polarized light, one of the enantiomers will turn in the light rotate the light, let's say 10 degrees to the left, and the other one will rotate it 10 degrees to the right. The degree is based on which enantiomers you're talking about, but they're going to be equal and opposite. One of them will move it a positive direction a certain degree, and one of them move it a negative direction a certain degree. And this is used or distinguished using a polarimeter. So let's talk a little bit more about how this works. So this polarimeter works by using polarized light. But what is polarized light? We hear the term polarized sunglasses. What is it? What's the difference between UV sunglasses and polarized sunglasses? So let's talk about it. So normal light vibrates in an infinite number of directions perpendicular to the direction of travel. So if light is traveling from left to right, the light is vibrating up and down. So it's perpendicular. It's going left to right, so it's going this way, but it's vibrating up and down. So when the light passes through a polarized filter, such as our polarized sunglasses, only light vibrating in one plane reaches the other side of the filter. So let's take a look at kind of a blown up view of some polarized sunglasses. Alright, so let's say you have some groovy rectangular sunglass lenses, and we see that if we got really close up on all polarized lenses, what it means to be polarized is that they have these tiny little black lines that run horizontal across the sunglasses. Now these are so small that we cannot see these lines with our eyes. If you get a microscope, you can actually see them. But with our normal eyes, we can't see all of these little lines. But what it does is it's going to block out one plane of light. We said light travels in a perpendicular wave. So if it's going in this direction, we said that it's going up and down. So notice that one plane of light, so if we have both directions going, one plane of light is going to be blocked by the horizontal lines. So the line that's going horizontally will be blocked by those horizontal lines. The line that's going vertically will slip in between those lines. So only one filter will be able to go through. So this is why polarized sunglasses work so well, is it's literally decreasing the amount of light hitting your eyes by half. It is taking out half of that light wave and blocking it from even getting to your eye. Now, what's interesting is that a lot of electronics only emit one of these wavelengths. And it happens to be the wavelength that is blocked by polarized sunglasses. So if you go to like the gas station and you try to read the price of gasoline at the pump, you know, they have the little screen with the price of gas. It'll look blank if you have polarized sunglasses on. If you take the sunglasses off, you'll be able to see the price. You put it back on, it completely blocks out that light. Some car panels. So if you have a car that has, you know, like the mileage or something on your dash, sometimes you can't read those because of your sunglasses. Pilot instrument panels. So helicopter pilots, airline pilots, they are not allowed to wear polarized sunglasses while they are flying because their instrument panel has that same wavelength of light that is blocked by your polarized sunglasses. So next time you go and check out polarized glasses, or if you have a pair, check out to see what gets blocked when you wear them. Now, the catch, or what's kind of cool to this is that you can actually see which glasses are polarized and which ones are not. So let's say you go to a swap meet and you know, there's a sticker on sunglasses that say these are polarized, and you go, I wonder if somebody just moved the sticker, or I wonder if these are really polarized. So what you do is you take another pair of sunglasses and you rotate it perpendicularly. So if this was a pair of sunglasses this way, so don't mind my terrible drawing, if you take another pair of sunglasses, so once again, terrible drawing, and these sunglasses now, when we turn them perpendicular, their lines are going this way. So then if we take one pair and put it over the other pair, so you overlap the lenses, it should go black. Because now you are getting rid of both wavelengths of light. So if you have two pairs of polarized glasses, you rotate one pair and you try to see through the lenses, you should not be able to see through it. If you can, that means one of them is not actually polarized. So give it a try. If you go to a sporting goods store or something, they a lot of times have polarized sunglasses, or a swap meet, it's super easy because they normally have them all laid out. But take a couple pairs and see if they're actually polarized. Alright, so let's get back to our polarimeter. So what the polarimeter will do is it puts in one of these filters in their light. We pass light through it, so only a certain wavelength of light can get through. Then we shine that light through our liquid and then measure how much it rotates. So if we take just any light bulb, here's all of the directions of light, we shine it through a polarimeter, only one direction gets filtered out, then we shine that through our solution. And when we do, we see that it is rotating that light a certain degree. So that's what a polarimeter does. It measures the degree of rotation of that polarized light. All right, so we said that one enantiomer always rotates the light clockwise, the positive direction. We're going to call this our D enantiomer, or D isomer. So I guess they do actually have a term. So let's see, it's dexrotary isomer, or the levorotary isomer. So L and D. So this isomer that also rotates counterclockwise, that'll be our L isomer. So under identical conditions, these enantiomers always rotate light in the exact same degree, but opposite directions. So for example, one of them will rotate it 10 degrees in the positive direction, the D isomer, and the L isomer then will rotate it 10 degrees in the negative direction. Now, if you have a mixture of these two isomers, we'll find it does not rotate polarized light at all because it cancels out. One will go with positive 10, one will go negative 10, so you won't see any rotation in polarized light. So it also tells you if you have a pure enantiomer, because if it's pure, it's going to rotate exactly where you expect it to be, or 10 degrees or whatever degrees it is. But if it's not pure, we'll see that it's less than that, and if it's a complete 50-50 mixture, it is a 0 degree rotation. Alright, so we'll stop there for part 1 of this lecture. So we'll, in our lecture, we'll be focusing on looking at what is our D and L enantiomers and being able to name our carbohydrates. In our next lecture, part 2, we'll look at a lot more at the stereoisomers and all of these chiral carbons.